So here's section 4.0 theorem 4.0.11 and then some things to go, an example to go with it. So we have A is n by n, and then you can say any of these three things. One, you could say A is non-singular if and only if the determinant of A is not 0. Now, since this is an if and only if, this is totally equivalent to saying A is singular if and only if the determinant of A equals 0. So these are really just theorems that are a consequence of all the work that's been done already. And then, of course, this becomes, because the fact that A is singular or non-singular impacts a homogeneous solution. It says then a third thing would be that the matrix equation AX equals 0 has a non-trivial solution. Again, if and only if the determinant of A equals 0. And so as a consequence of everything that's been done in chapter 4, any of these three statements is equivalent to the other two. So if we know one of these, we know the others. And that's the point of that theorem. Okay, now, so an important application is that I would like to know when the determinant of A minus some constant lambda times the matrix I, the identity matrix, is equal to 0. Okay, so what you're asking is again similar to these. So I'm asking, okay, when is this matrix singular? But the reason one wants to know is that we would like to know if there are any non-trivial solutions to this equation. Now, where does that come from? Well, actually, it comes from solving the equation AX equals some constant times X. Okay, because if I multiply through by X, and I just get, identity times X is just X. And so then I move that negative over to the other side, and we have this. So you see, it's asking what values of X, what vectors would be affected by a matrix multiplication of A, similarly to just multiplying that same vector by a constant. Interesting question. So that ends up being a very important application of this. And so, for instance, I could just do something like A equals 2, 3, and 5, 4, something like that. And so then I'm asking, when is the determinant of 2, 3, 5, 4 minus lambda 0, 0 lambda equal to 0. When does that happen? Well, I'll put these together. I have the matrix, so I want the determinant, so I'll just use the straight lines of 2 minus lambda 3, 5, 4 minus lambda. I want that determinant. Well, I calculate that determinant with 2 minus lambda times 4 minus lambda and then minus 15. And so notice what happens when I do this. I get a polynomial. Now I'll have to do this minus 15, but I can see, because that's just a constant, I'm going to get this from those a quadratic polynomial. I've got lambda squared minus 8. Is that right? Minus 8. No, minus 6. Whew. Minus 6 lambda. And then plus 8 and minus 15. So this is lambda squared minus 6 lambda minus 7. And I would like to set that equal to 0. And so I can solve that quadratic. Can I factor that? Minus? Yes, I can. How about that? I didn't know I'd be able to factor it, right? This is lambda minus 7 times lambda plus 1 is equal to 0. So lambda equals 7 or lambda equals negative 1. Okay, so I can tell you that for that lambda, now I don't know what x, what the vector x looks like, but I can solve that as well. So I go back here to this matrix, and let's use the negative 1 first, lambda equal negative 1. And so I would be solving 2 minus a negative 1, that's 3. And then 3 and 5 and 5. You should, I mean, if you don't get a matrix that's non-singular, you did something wrong, because remember, that's the whole point. We did this so the determinant would be 0. So I have that matrix. If I go ahead and do a reduced row echelon form of that, right, it's pretty obvious, I hope, that I get 1, 1, 0, 0. Okay, so that's my reduced row echelon form. If I augmented that with zeros, for the homogeneous problem, what I see is that, this implies that x equals minus y. That's my vector. So a vector that would work for this would be, well, let me write this as x1 and x2 since I'm going to use an x. So a vector that would work here would be the vector x equals 1 and negative 1, or negative 1, 1. So let's try that. Okay, so let's take our original matrix, 2, 3, 5, 4, and multiply that times 1, negative 1, and see if we just get a multiple of 1 and negative 1. Well, we get 2 minus 3, and then 5 minus 4, which is equal to negative 1, 1. Yes, right? That's the same thing as negative 1 times 1, negative 1. So there we did it. And similarly, if we let lambda equal 7, our matrix was 2 minus lambda, so that's a minus 5 and a 3. And then we had a 5, and 4 minus 7 is negative 3. And so again, if I do a reduced row echelon form, well, certainly I get a -5 and a 3 and a 0, 0, and then divide through by the -5, and I have a 1, -3/5, 0, 0. And so, here is saying x1 equals 3/5 x2. And so, for instance, if I let x2 be, 5/3, then x would be 1. But probably a nicer one would be let x2 equal 5, then x1 equals 3. Okay, so I could have my x then be the vector 3, 5, and that will work. I'm just, so notice there are infinite number of vectors that would work, but I want one that's nice. And so again, let's take our 2, 3, 5, 4, our original matrix, times 3, 5. And what we get is, 6 plus 15 up there, and 15 plus 20 here. That is 21 and 35. And so you see that's just our original vector there, 3, 5 times 7. So there we did it. Okay. So as I said, we're going to see in after the next chapter, so in a couple more chapters, that this particular question of, when is, for a given matrix A, when is this determinant equal to 0, is an important question. But you can kind of see that certainly for 2 by 2 matrices, I can answer that by solving a quadratic. If you go to 3 by 3, I'm not going to go through this whole thing, but if I go to a 3 by 3 matrix, notice that, and I'll just put the minus lambdas in there to begin with. So suppose I had a 2 minus lambda, a 4, a -1, 7, 1 minus lambda, and a 3, and maybe a -2 and a -6, and a 5 minus lambda. Okay, so if I had something like that and I wanted its determinant, notice that what's going to happen is I'm just going to get a polynomial again, in this case a cubic, because I will have the 2 minus lambda and then times the determinant, so that minor, that 1, 1 minor, this determinant down here, and so that is going to be 1 minus lambda times 5 minus lambda, and then plus 18. And then minus a 4 and dot, dot, dot. We're going to do all that. Now, the reason I'm not doing that is well, I would just go to Sage Math and type this thing in and ask for the determinant of it. I wouldn't. I'd probably use a t or an x or something, not the lambda, but I would do that and get that. And similarly, I would probably use Sage Math to do the reduced row echelon form stuff that I did here. This kind of stuff. Just get it to do that calculation for me, and not a big deal, right? So. Well, oh yeah, need to solve a cubic equation. I would probably get Sage Math to do that for me as well. Or you could, once you have this polynomial, you could at least get a numerical approximation of lambda, if nothing else, by using something like Desmos to plot that and determine what lambda might be. Okay, so that is, again, back here to, this theorem, 4.0.11, about, matrices being singular and determinant 0 and so forth, but also the non-trivial solution. And so This is just one application. Um, they they give examples similar to this, but not exactly this. But they give some unknowns and take the derivative, or sorry, take the determinants, and so once they do that, they get something kind of like we did. They get an equation in their unknown. It's just for our particular situation. We will always get this polynomial. Well, I guess in their case, with their unknowns, they would get polynomials as well. And there we go. That is theorem 4.0.11.